Problem 614. Link 2 is isolated from a kinematic diagram and shown in the figure. The link is rotating clockwise, driving point A at a speed of 40 feet per second. Determine the velocity of points A and B and the angular velocity of link 2. Use gamma equal to 50 degrees and beta equal to 60 degrees. So let's start the problem out by writing out a couple of the values we know. We're given the linear velocity at A is equal to 40 feet per second. We're given, right, this is just a magnitude, hence we have specified it with this lowercase v because we weren't given a direction, just a speed. Let's go ahead and let's convert this to inches per second, just in case we're going to need it. And this is 480 inches per second. We're also given gamma. Gamma is equal to 50 degrees, and beta is equal to 60 degrees. Okay, let's do a little bit of a free body diagram overlaid on our image here. So first let's draw VA in its general direction. Right, we know VA is going to be 90 degrees off of the link that connects it to the link to the point of angular velocity, right? We'll call that C, this pin down here connected to the frame. So it's going to be 90 degrees off of AC. So we'll draw it in this orientation. VA. And again, this is given a capital V because it has a direction. We'll also go ahead and draw VB. We know that VB, again, will be 90 degrees off of that length BC. Draw that. And that's our VB. Okay, so part of what we're doing, right, is finding not just the magnitudes but the orientations of these velocities. So let's give us a reference axis to go off of here. Simple enough. XY. Let's give us reference axes here. We'll draw our x-axis at both points, and we'll label these angles. We'll call this angle between our reference x-axis and VA. We'll call that theta, and we'll call this angle up here between our reference x-axis and VB, and we'll call this angle phi. So what we should look at doing next is solving for these two angles. So for angle theta, so if we look at theta is 90 degrees off of that length AC. And AC is rotated gamma degrees, or 50 degrees, off of the horizontal. And that gives us theta equal to 40 degrees. Okay, let's do the same kind of thing for phi. So phi, right, based upon this length BC, well, BC is rotated gamma plus beta, or 50 plus 60 degrees. And then phi is 90 degrees off of that length BC. And this gives us phi equal to 20 degrees. Okay, so now we have these angles. One of the things we need to solve for is we need to solve for the angular velocity of the entire length. And solving for the angular velocity will also help us solve for the linear velocity VB, because we know the length VB is away from our center of rotation C. So we're going to use the equation that relates linear velocity to angular velocity. So V is equal to R omega. And if we rearrange this, we'll see omega is equal to V over R. Okay, so let's use this. So omega is equal to, and we know, right, we know VA, and we have it in inches per second. So 480 inches per second over R, 8 inches. And this gives us omega equal to 60 radians per second. So to rewrite this with a little more space, omega is equal to 60 radians per second, and it's moving clockwise. Okay, so this is one of our answers, but not only is it one of our answers, it's going to help us solve for VB. So let's solve for VB. Well, VB, the magnitude of the velocity at B, is equal to 18 inches multiplied by 60 radians per second. Right, jumping back up to our V equals R omega equation. And now we're going to want this velocity in feet per second. Feet per second, it's just cleaner. It's just more of a standard measure of velocity. So we'll go ahead and we'll multiply this by 1 foot over 12 inches. And this gives us VB equal to 90 feet per second. Okay, so now we have the magnitude for VB, so we just need to write it out in its full vector format. And we have the angle, right? We have the angle that it's based off of our x-axis, right, in phi at 20 degrees. So VB is equal to 90 feet per second at 20 degrees. Now this is kind of just a way to write angular notation when we're specifying a vector, just kind of offhand. When you're solving problems like these, this is an acceptable way to show me 20 degrees. You'll notice that our arrow is oriented in the direction off of the horizontal that VB is also oriented, so it does give us a complete picture of how VB is oriented. Let's go ahead and write VA. So the velocity the velocity at A is equal to 40 feet per second, and it's oriented 40 degrees off of the horizontal. And again, we see that, right, this angular notation, the arrow is also pointing in, right, the orientation of A and giving us that 40 degrees, giving us a complete picture of how VA is oriented. And there you have it. So we solved for VB, VA, as well as our omega, thus completing the problem.